is nonlinear dynamics, PT symmetry, and supersymmetric quantum mechanics. So please, Subhrajit, you can share your slide and go ahead.
Yes. So my screen is visible, right, Aradhu?
Yes, 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 it is visible.
Thank you. Just let me share my screen first. Yeah. Okay. So is it visible properly?
Yes.
Yeah. So let me know when to start.
Yeah, you can start.
Okay. So first, I would like to thank Professor Panigai for this chance, and probably there is a correction, Aradhavaya, because I have shifted my field from PT symmetry, supersymmetric quantum mechanics to quantum information theory.
Okay.
So yeah. So as you can see, so the title of the talk is Saturating Quantum Advantages in Post-Selected Metrology with Positive Kirkwood-Dirac Distribution. So people attending this seminar, actually, they might be familiar with the terms like metrology and quasi-probable distribution, but this post-selected metrology and Kirkwood-Dirac distribution seems a little unfamiliar. So I will describe all the things.
Subhrajit, there is a, I think, small screen at your slide. I think. Yeah, please remove it.
Right.
Yeah. Okay.
Just a minute. Just a minute. So is it properly visible now?
Yes, yes, it is visible.
Yeah. So, right. So this is the tentative outline of my talk. So I will first describe what is Kirkwood-Dirac quasi-probability distribution is and how to define the notion of non-classicality via this quasi-probable distribution. Then I will introduce a little bit about quantum metrology and will describe more about post-selected quantum metrology, what are the possible quantum advantages that you can get from this kind of setup, and how to bound such quantum advantages, and what are the possible source of such quantum advantages. So probably I will precisely focus a part of the whole theme on the notion of the non-classicality, because there is a time limit. I need to finish within 30 minutes, right? So now, yeah. So now, as you know, there are the very common notion of non-classical distribution, like the one is the Wigner distribution and one is the Glauber-Sudarshan P distribution. But around 1930s, Kirkwood also came up with a distribution which got further contributed by the Dirac. And after this is named after this Kirkwood and Dirac, and this is the Kirkwood-Dirac quasi-probability distribution. So before going to the details of Kirkwood-Dirac quasi-probability distribution, I will let you know. So what is the difference between probability distribution and quasi-probability distribution? So quasi-probable distribution relaxes some limit of classical probability distribution, right? So they can take negative values, they can take complex values. So now, in general, the notion of non-classicality refers when you are having a negative element in your probability distribution. But main theme of my talk would be, is it really true in every set of protocol? So let's see. Yes. So what is this Kirkwood-Dirac distribution and why it is so special? So let me tell you. So I am just bringing this Kirkwood-Dirac distribution is not as a general scenario. This is just to investigate our case in the context of Kirkwood-Dirac distribution. You can also recall different other quasi-probable distribution, but here I will focus only on Kirkwood-Dirac distribution. So suppose you are having an arbitrary state and two non-commuting observable, this A and B. And suppose I'm imposing a more restricted condition onto this. A and B are non-commuting, not only this, rather the member that constitutes the A and B are also non-commuting. Like you can see the last point that M and Bn are non-commuting for every value of M and N. So now what would be useful from this assumption? So now you can see if you are having this kind of setup, this kind of measurement setup, any state, you can see the first black box. Sorry, I don't have the marker to point out. You can see the first black box. Any state can be expressed as a distribution, which is defined as P as a function of M, Bn. So this is the Kirkwood-Dirac distribution. So how does it look like? you can see the second box, which is marked in green. This P, AM, BN looks like trace row over AM and BN. So if you decompose the trace element, you can see this can take the complex values. And if you go to the first box, the other term apart from this P, AM, BN, in literature, it is known as the conditional state that is coming out from the successive projective measurement. So what is the speciality in the Kirkwood distribution? You can see this is a complex value distribution. And if you take the marginal, they are giving exactly like the classical distribution. Like suppose if you sum over M, the whole distribution, you can get the trace rho BN. And the similar thing when the summation is running for N, right? So this is the case. So now you can see it might seems to you like it's a joint probability distribution, but in a complex sense, right? So this is more or less the case for the Kirkwood quasi-probability distribution. I won't go into the detail, but if you need to know more things on the Kirkwood quasi-probability distribution, you can get back to the other slide and see the references, right? So now the question, how to realize or how this kind of quasi-probability distribution is being manifested at the level of operation. So these are few slides. I'm not going into the details. These are the slides just to make a sense how you can feel this kind of quasi-probable distribution in terms of successive projective measurements. So these are all the details. So if you have any question after the talk, you can ask me. I will go into the slides. So this is not required for the technicalities. This is just for making the intuitions. So these are the things. So now I will start from this. So now, as you already know, how this Kirkwood quasi-probability distribution looks like. So this Kirkwood quasi-probability distribution can also be expressed in terms of few things. Now, what are the things? Now, if you see the first term is the real term, right? So now you can ask me how this first term is coming from. So for the technicalities, just leave this part. So this part won't hamper the tempo of the talk. And the second part, you can see what is this rho and rho prime. Rho prime is the state that you are taking at the very first stage, and rho prime is the state that is a post-measurement state when the measurement is done for the operator or for the system observable A. So now you can see the second part of the right-hand side, the second term on the right-hand side, it's like an expectation value of the observable B with respect to a state which has no measurement upon it, and the expectation value of Bn with respect to a state which has some intervening measurement with respect to A. So now this is just a clever trick to write the whole distribution. So we are just composing the total distribution in terms of real and imaginary part. These are all the notations. Now, at least for the talk, these are not that much necessary. So now you can see what I will conclude as I have stated at the very initial, that real value of the quasi-probability distribution, which is the Kirkwood quasi-probability distribution, is need not to be negative just to have some non-classical advantages. Rather, you can have also positive values, and through this, you can also get some non-classical advantages. So now we will set some more restricted condition, but this restricted condition is not general condition. This condition is coming out from a particular protocol, and the condition would be like the last one, which is written in red. So now I will show you how to have this condition or how to realize this condition. So this is the second part of the outline. Now I will go to the quantum metrology. I will not go into the detail of quantum metrology and post-selected quantum metrology. Rather, I am more interested in showing this, how this notion of non-classicality is becoming a little confusing in the different context. So these are all metrological setup, you know, because metrological experiment refers for some parameter estimation protocol, and you have to design different many protocols through which you need to minimize the error in estimation. So there are many protocols. There are classical metrological protocol, there are quantum metrological protocol, and there are different many things. You know, so now you have to decide how to engineer this kind of protocol so that you can have a minimum error in the estimation. So these are all the classical camera bound and Fisher information. You know, this Fisher information is the quantifier in deciding the error. So this is the protocol, and this is the quantum metrological protocol. How this expression, this IQ theta, is the Fisher information. And mostly all throughout the protocol that I am designing or I am stating, this is done for the PO state. There is no notion of mixed state till now, right? So this is just a normal extension of quantum Fisher information from the classical Fisher information. So now I will show you what is this notion called the post-selected quantum metrology. So before going to the post-selected metrology, you can see one thing. The expression IQ theta, you can see the extreme right-hand part. It's like a 4 into variance of the system observable with respect to the initial state. So now you can see whatever optimization you can do, you can't beat this. You can't beat this variance. This delta small a square is nothing but a difference between the largest eigenvalue and the smallest eigenvalue. So this is the limit, right? So that you can't overshoot. So all the limits that I'm talking about, this is for the infinite many trials. These are all the statistical limit, right? This is not some limit that you can touch for a particular trial. These are all the statistical limits. So you have to run numerous number of trials. So now I will describe about post-selected metrology and quantum advantages. So what are the quantum advantages? So quantum advantages in this context would be like, so you are overshooting the limit for a particular trial, and we will find the reason why this is happening. So more or less, this is the case. So yeah, so this is the standard post-selected metrological protocol. So look, the preparation of the state, that is very much similar, just you need to prepare in the PO state. Then there is a encoding procedure. So there, the encoding procedure is strictly unitary. Well, so now after encoding some parameter, you are receiving the state as psi theta. So, so now what is the difference between the ordinary quantum metrology and post-selected quantum metrology is after having the state, after the encoding, so you need to run your state through a post-selection block. After receiving the state from the post-selection block, you need to do all the measurements. So there is a change, right? So you can manipulate your post-selection in a way so that you can gain more information. So let us check whether it is really possible or not. Right now, after having all these technicalities and writing all the post-selected state, post-selection blocks, and post-selected quantum Fisher information, this looks like this, right? So now you can see, so what I have already said earlier. So I will now hit the quantum advantage in some limit. I will show you how. So the quantifier of this quantum advantage would be your IQ theta condition on psi theta PS, which is the post-selected state, is not bounded by the limit that is set by the Heisenberg. Okay, so you were overshooting the limit, but you are not overshooting the limit statistically. You are overshooting the limit for a particular trial. So it might also be possible that after having all the data, you can't feel any kind of advantages. But at this level, the overshooting is done for a particular trial, right? So yes. So now, so I am not going into this, right? I am not going into this because these are all defining those metrological efficiency, how efficient our protocol is. So now you can see, because when you are having this weak measurement kind of setup, when you are having the post-selected states, you can write your expression in terms of weak values, right? So now when you are having weak values, you know, higher the probability of having larger weak values, lower the probability of having successful post-selection. So there is always a trade-off between the successful post-selection and higher the weak value. So if you want to get a particular term higher, you have to lose the successful post-selection probability, right? So there is always a trade-off. So now what we did, we tried to compose the term in a way so that it can define how efficient our metrological protocol is. So this is all, everything is written in terms of this Kirkwood-Drake quasi-probability distribution and others. These are all technical terms. I'm not going into the details because my theme of the talk is not touching these technicalities. So I will skip the slide. Right. So this is the metrological efficiency that is written in terms of weak values and Kirkwood distribution. So now you can see one thing. So whatever I have written previously, that QIQT quasi-probability distribution can be composed of two terms, right? One is real and one is imaginary. So that is all, everything is just a sophisticated playings of this parameter. So you can also define this kind of term from this expression, and you can write the whole expression through this term, right? So as you can see, the first term in the green box and the left-hand part is the QIQT quasi-probability distribution. First part at the very right-hand side is the Wigner formula that is purely real. And the third part is nothing but some term that is coming from the non-commutation of the observer, right? So suppose if there is no non-commutation between your observables, so you can't see any effect of non-classicality, right? So the last term, the very last term, is actually counting when the ordering of the observable is not reversible, what amount of correction it is giving to the original formula, right? These are all the nomenclatures, right? So now these are our comments. For pure states, the metrological efficiency is 0 when its KD distribution equals to the corresponding Wigner formula. Now it seems very much clear to you, because when this AM and FK are commuting, the correction term from the third bracket would be 0. So right, there is no non-classicality and there is no quantumness. So the metrological protocol that you are building to have some quantum advantages, it will not show anything, right? So this is the remark that you can see. For pure state, the metrological efficiency is 0 when its KD distribution equals to the corresponding Wigner formula. So now I have told you earlier, the KD distribution can take complex values, can take negative values. But the Wigner formula, which is written by capital Q, that is purely real. So when this KD distribution equals to the Wigner formula, you can see, you can use the cyclic property within the trace, and you can have the last term equals to 0. So far it is clear that if you are having two observable like AM and AFK, which is commuting, there is no metrological efficiency coming from your protocol. So now let's get into the next part of my talk, right? So these are all the optimization protocol, how to optimize the advantages, so I'm not going into the details, right? So now you can see this is a theoretical design of a metrological protocol that is based on our previous prescription. So I have written a generator, I have written the post-selection log, and I have written, so what would be the rank of the projector for the post-selection. These are all the things. What is the initial state? These are all actually chosen very much carefully, keeping all the conditions maintained. And what would be the final states, you know, because just you have to run a unitary operator onto Xi, so you will get the final states. So, and now what you have to guess, you have to minimize the parameter del theta by properly choosing or by some proper estimation. So these are all the protocol, these are all the things. So now let me go into the next slides. After having all the calculation, what you can see the just last black box. So now you can ask me the question, why you are imposing the limit. This imposition is only because of the optimization procedure. So that I want to check when the Fisher information is higher, what is the associated or the corresponding probability in the successful post-selection. So these are all the things, the optimality condition. Now you can see when you are having the alpha value pi by 2,
Subhrajit, you are not audible.
Yeah, maybe we lost him.
So Dhirendra, are you here? Can you call him, Subhrajit? Yes. Do you have his number? I don't have his number. I have his old number, but I don't know, is it working or not? Let me check.
Yeah, he seems to be done. No? The talk is almost over, right?
Yeah, I think so, sir. Yeah, it is
Yeah.
almost over.
Almost over.
So, yeah. So, can we go to the next speaker? I don't have his number, so I don't know. Let me-
Okay, his WhatsApp number seems to be ringing.
Okay.
Hello?
Yeah. Please.
Yeah, Abhinav here. His
Yeah,
WhatsApp number seems to be ringing, but he's not picking up.
Okay, so I think we should go to the next speaker. So shall we start? Or we should wait for
Okay.
Okay, so sorry for this interruption. So we will go to the next speaker. So the next talk will be delivered by Dr. Kumar Vino. Abhinav is currently working as an assistant professor at University of Mahidol, Thailand. He did his PhD from ISER, Kolkata. After his PhD, he was a postdoc at SN Bose, Kolkata. Then he went to Turkey for his second postdoc. I have known Abhinav since 2011, and we have written several papers. I really admire his dedication toward research and his clarity of thoughts and collaborational ability. I have learned a lot by interacting with him. So his area of research are quantum field theory, nonlinear dynamics, and PT and supersymmetric quantum mechanics. So Abhinav, you can share your slide and.
Yeah. Okay. 1 second. Okay. Can you see my slide?
Yes.
Yes. Okay. So first of all, thanks to the organizers for giving me this opportunity, and thanks a lot, Aradhas, for this introduction. I don't think I deserve most of it, but I have learned a lot from you also. So it puts me under a lot of pressure for this talk. But what I'm going to talk today is something I did long back with Professor Panigrahi and Professor Arun Jainavar from IOP Bhubaneswar. And we are actually trying to look at some new possibilities out of it. So this will be a simple exposition of whatever we are thinking or I am thinking. So let's see. First of all, there will be some introductory part regarding PT symmetric systems. So please bear with me if some students are there, they can take some benefits. Okay. So I'm stretching on some non-local correlation in PT symmetric systems and the possibility of entanglements. Okay, the two phrases non-local and entanglement kind of rhymes together. So it's a obvious kind of line of thought. So let's proceed.
Can you go to the full screen mode?
Yeah, I can. One second. One second. Let me just reshare again. 1 second. Wait. Let me share screen. 1 second. Stop share. Okay. Am I sharing properly?
Yes.
Yeah, you can see me, right? Okay. Just give me a second. There is some small problem, I guess. Okay. Yeah. Okay. Is it very small that I'm asking?
No, it's okay. Okay, go ahead. I think
it's okay. So I can go to full screen. Yeah. Okay. So 1 second. What is happening? Wait.
If not, then you
okay. It's okay. Okay, sorry, there is some problem with the key. So the plan is like there will be overview of PT symmetric systems. Then I'll be talking about PT symmetric scattering, followed by two-level analog for whatever I'm talking about. And I leave with certain possibilities. So it will be an open-ended talk in that sense. Right. So what is PT symmetric system? So before that, let's understand what happens if you have a complex Hamiltonian in your hand. So automatically we can see that from this equation that if you look at the energies will be complex. So there will be imaginary part, and because of that, this so-called unitary evolution in here, the second term you can see there will be a plus minus real phase, means there won't be any I. So your amplitude can decay or rise. So that is the gain and loss concept from PT symmetry. And so that was expected. It was seen in everywhere. Whenever we have a lossy system, mostly in physics, you don't see gainy systems. That was okay. But for certain such complex Hamiltonians, if you don't have gain or loss, then it's surprising, or rather you have real eigenvalues. So such Hamiltonians are classified under PT symmetric Hamiltonians, and they are systematically studied by Bender and Bocher in 1998 in their famous paper. And it means that you the system is not Hermitian, or the Hamiltonian is not Hermitian. As you can see in there is a here there is a IX term here. So, but it is symmetric under parity, which is the space reversal, and time reversal, which changes t to minus t, but also I to minus I, because it has to be anti-unitary. And why it has to be anti-unitary? That you assume that energy is, if energy is positive of a system, it should stay positive under fundamental transformations like time reversal. So, okay. So next, the interesting systems are those which are actually not Hermitian but PT symmetric. See, all the Hermitian Hamiltonians are essentially PT symmetric. So we want to look at the non-interesting ones, which basically commutes with the P and T, but they don't show Hermitianness. So there are two phases. Those are parametric phases, and the parameters are found in the Hamiltonian. The broken phase is characterized by complex eigenvalues, and that is kind of expected. And there the eigenfunctions for complex conjugate pairs are PT related, that from one to the other you can go through PT transformation. But in the interesting phase, which is the symmetric phase, where energy eigenfunctions are real, and you can automatically see that the eigenfunctions are actually also the eigenfunctions of the PT operator. That's very easy to show, and it definitely contradicts what we know from Hermitian quantum mechanics, that you are getting real eigenvalues out of complex Hamiltonians, or in general non-Hermitian Hamiltonians. So okay, so these systems are experimentally studied and like rigorously shown that we observe actually real structure. Like in optical systems, we end up with systems without gain and loss, and the Hamiltonian is always PT symmetric in those cases. But to do quantum mechanics, you have to define a scalar product. Like, okay, you don't need states. You can go to maybe the Heisenberg, you can go to density matrix representation, or you may say that we have Heisenberg representation. For there also, to find out matrix elements, you have to take a scalar product. So the norm itself was found that if you take simply an expectation value of PT, like here, if you take an expectation value of PT, it is within that given state, it's which actually turns out to be the norm in this system that we'll see. That's not a semi-positive definite. So the interpretation of probability, which is positive, that requires that you introduce one more operator, which is called the charge conjugation operator, but it has nothing to do with that. Just it looks similar, which you introduce additionally, and that constitutes a positive definite norm. So okay, so next, what you do for observations. So for that, we need a more general formalism, which is people have talked about, the pseudo-Hermitian formalism, where you define a metric operator, this eta. So just a second. Yeah. Hello. Yeah. So that metric operator is required to define a positive definite norm for such systems, and that metric operator is Hermitian. So that Hermitian operator appears in the scalar product like this, that you put any observable operator just towards right of the metric operator. So I'm following here the notions of this paper by Mustafa Zadeh. So that is the most common notations, I guess. So next, so Aradhya, I am audible, right?
Yes,
Hello?
yes.
Okay. Please stop me if there is any problem.
Yeah.
So the norm is semi-positive definite, stationary, and it is also orthonormal, and we get real spectra, so we are happy with it. And for PT symmetric system, if you try to construct a pseudo-Hermitian structure out of it, so we end up with an expression which is this, that the norm operator turns out to be the inverse of C and P to the power -1. So C actually is expressed as e to the power. So C is equally expressed as e to the power some Q operator into P. So once you multiply it with P, it is e to the power -Q because there is a to the power -1. And so you may ask, who has the time reversal operator? Okay, so once you take the transpose to create the bra from a cat, so that time reversal effect is absorbed in there. So the problem is that for most of the systems, unless you are dealing with pure spin systems which have only 2 levels, or finite dimensional system like maybe angular momentum value 1 or something like that, for continuous systems, constructing this Q operator is really difficult. And there are perturbative methods and other methods are there. You cannot actually prefer any one of them. For any continuous system, for very simple ones, in fact, they are really difficult. So you can go through references there. So next, we'll talk about this PT symmetric scattering I mentioned. So what we see that there will be a non-local correlation conservation. So why we are bothered about scattering? Because when we were working on this paper, just before that, certain experimental and theoretical results came out for certain laser systems. One was this CPA. So CPA is coherent perfect absorber. So it was seen that if you have certain laser signals arriving in a medium with a complex refractive index, under certain conditions, the light was completely absorbed and nothing was emitted. In reverse, it was seen that it is more interesting that if you have PT symmetric structure in certain materials than in refractive index, obviously it's an optical system, there if you excite the system under certain parametric conditions, suddenly it used to give out laser lights. But in both cases, the signals cannot be a single one. There will be two signals coming in or going out in both ways. So that was kind of a peculiar behavior. People saw it and they knew PT symmetry has to do something with it. So we tried to analyze it directly. And how? We considered the Schrodinger equation. And why? Because under paraxial approximation, optical systems are actually, they follow a Schrodinger equation. Just you have to identify the variables. So let's consider a generic PT symmetric system and the Schrodinger equation. So there, the interesting thing is the potential, that the potential is PT symmetric. And we are considering a stationary potential because those what you realize in real physical systems. So under space reversal parity, x goes to minus x. And because there is no time, only thing you can do, you can take the complex conjugation. So there is a star. So the potential is unchanged under that. So it's a non-Hermitian system. It's a PT symmetric system. So next step is that you take complex conjugation and parity successively. I'm not saying that you take time reversal. You don't take time reversal. You take complex conjugation because first we want to actually cancel the potential so that we end up with an equation of continuity. And the second, the potential is time independent, so it's the same thing for the potential. So what you end up with, you can see that in the right hand side of the equation, you end up with some quantity with a total time derivative. And that we can call as a charge, local charge density. And if you do a space integration for well-behaved fields, the left-hand side will vanish. So the right-hand side will give us a total derivative of some quantity, and which will be conserved because the left-hand side will be 0. So, but this conserved quantity is by structure, it is non-local. This charge is non-local because it relates 2 points x and minus x. So I am again stretching that you are taking complex conjugation, but not full time reversal. And that's because the potential was so, and we encounter such potential. So this treatment result is very much general. So if you have a charge density, which is like this, you can define a charge after space integration like this, so which will be basically an expectation value of the parity operator, nothing more than that. And it is by construction, it is conserved. So now remember one thing, that the Schrodinger equation is still valid, and because the Hamiltonian part is still valid, with respect to this Hamiltonian, the evolution of the states are still unitary. Remember, the scalar product is different, but the evolution is unitary in this case. So we can take out the unitary time evolution outside from the states in the definition of the charge, conserved charge, and from there we can have something like that Hamiltonian commutes with P, because these parts can be arbitrary. So the commutator is arbitrarily true, but that is not a statement that the Hamiltonian is parity symmetric also. That will be a stricter condition. Why? Because this evolution of the operator is not a unitary evolution, because see, the unitary evolution of the operator comes in the Heisenberg picture from Schrodinger picture if you consider the scalar product, and the scalar product here is different. So unless you introduce a norm, this cannot be an evolution of the operator. So at a particular time, this may be true that the commutator vanishes, otherwise it is not. So in other way, that the norm is different. But we are not bothering about the norm right now. We will be concentrating on the scalar product, because that quantity, this scalar product, is fundamentally conserved. Actually, if you have noticed, this scalar product is nothing but this conserved correlation, I should say correlation, that is nothing but the wrong PT symmetric norm, which is not semi-positive definite, that Bender et al. First arrived. And then you introduce this charge conjugation operator to fix the problem. But we are using it without fixing that problem, that we are saying that, okay, this is not the probability interpretation, but this is something which is fundamentally conserved. Okay, so with that idea, now by construction, this quantity is non-local, and just a detour that if you consider eigenfunctions psi of the Hamiltonian, in that case, you don't end up with a conservation, rather you end up with a two-layer condition that either energy is real, that is the case when PT symmetry is preserved, then you cannot say that this quantity is this P, this scalar product is like 0 or non-zero. But when energy is complex, then obviously this scalar product should vanish. So PT symmetric phase, this scalar product is interesting, but it is not conserved in a sense, because there is no time derivative. So it's like the absolute value of the scalar product. So basically what is happening, that the time derivative for eigenstates are bringing out this E minus E star actually. So what is happening? So right, so more so you can see that in the symmetric phase, because the wave function is PT symmetric, the current that I mentioned earlier, this current part, yes, this the left hand side of the first equation, you can see this will vanish definitely because of PT symmetry. That means quantum mechanically it will be some kind of a bound state, quote unquote, where let's see what happens actually. So let's consider the scattering property, that if you consider localized potential, you can talk about asymptotically plane wave kind of solutions, and these are the nomenclature that we established. So if you have identical plane waves, which is a PT symmetric combinations arriving from two different directions, so we see that the current is 0, and there is a possibility that there is no output. If such plane wave are inciding from left and right, there is no output, and because of that the system is like absorbing everything. So that can be an explanation of what coherent perfect absorber was, which was observed experimentally. And you can take a reverse of this thing, which is the inversion, that you consider again a PT symmetric combination, that two identical plane waves are leaving the system on both sides. So that can result from again from a conserved zero current scenario, which is like a say at the beginning there may not be any signal at all. The system, out of maybe some thermal excitation, it's giving out two opposite beams, which is actually the proposed PT CPA laser in that sense. So kind of this consideration of PT symmetry with the correlation, if you consider this correlation and the corresponding current, it explains actually these physical phenomena in that sense. That So again, the condition is that this confirms our earlier inference that this overlap may not be zero. Something is conserved, so that thing is staying inside and giving out the signals. So for the PT broken case, in case you can, you may not have this identical plane waves, but plane waves with different coefficients, right? They have to be, because plane wave itself is PT symmetric, e to the power ikx. So you need coefficients to be play in a role to make them non-PT symmetric. So that will be the broken phase, which is not interesting for us as of now. So we further saw that if you take some localized states, what do you mean by localized states? That either you consider the left side or the right side of this potential. So those are localized states. For them, you end up with, for PT symmetric system, you end up with a Hermitian scattering matrix. This S is the scattering matrix. And the transfer matrix satisfies some condition like this. Okay, which is, you know, for real systems or Hermitian systems, scattering matrix is actually unitary. It's not Hermitian. So, and also if you have a potential dies down to the real part actually dies down to a constant asymptotically and the imaginary part vanishes, then you have something called duality condition, which is actually observed and known in optical systems even before, for long before. But for most interesting, if you take the states to be non-local, that one state is from left, the other state is from right, these two, so-called in state and the out states also from left and right, both. In that case, the scattering matrix satisfies a condition which is this, that it is not unitary, definitely. It is not Hermitian also, but it satisfies a case where it sandwiches the Pauli matrix, the second Pauli matrix. So which is actually like charge conjugation operator actually. You can like charge conjugation effect, that is in terms of scattering matrix, it looks like this. So you can finally write down that scattering matrix, actually you can identify this sigma 2 with this eta operator, the metric operator itself, the pseudo-Hermitian one. So which is this, as we remember. So what is happening that if you consider the non-local combination, we get a pseudo-Hermitian algebra automatically. So this non-local combination is actually quite close to, or it is representing the actual PT symmetric structure, what we are talking about, the symmetric phase. So okay, so our inference is that we have this in-out combinations, which actually gives preserve the non-local correlation and gives you the observable results, which it explains well, and like it this conserved correlation is kind of a unique thing that is there for PT symmetric systems. Okay, so just one example that now let's go back to the simplest example of PT symmetric system that people use very commonly, which is the two-level system given by this Hamiltonian. And there actually you can see the energy eigenvalues has a square root part, so this so it can result into a complex eigenvalue. So the states are like this, and this alpha is a parameter which is defined in terms of the earlier parameters, which are real. So these eigenstates, two eigenstates, to define a real norm, you can construct this charge conjugation operator, and this charge conjugation operator is easier to construct for two-level systems. So you can construct it. So the inner product is well defined and everything, and people have studied Bell inequality and like entanglement properties with this reference I have given. So that is one of the references with these kind of systems. Okay, spin systems, you can consider it easily. But now if you consider, don't consider the scalar product, but the scalar correlation, not the norm, the correlation we are talking about, we have calculated for these states. These are just plus minus 1. So they are constants. So it's not positive definitely, but it's a constant. So we have this conserved correlation in this form for this simpler system. So right, so what we can do, so can we do something, can we construct something that will allow us to utilize this conserved correlation to look at something like entanglement, like say Bell inequality or something. So with this conserved correlation in continuous system, which is really difficult because you don't know how to construct the C operator given a potential in a general way. That depends on the system. But there is a formulation. So it is given in this paper that I'm mentioning in the bottom. So you can construct a spin algebra out of continuous variables, any continuous variable. Let me consider the position position basis. So you can define projection operators like P and T like this. So T is just a shifted projection operator. How? By segmenting your real axis into or real space into segments, infinite number of segments of length L. Okay, so from this definition, actually you can construct the spin operator. This is the Z component, and these are the S plus and S minus operators, and they satisfy the algebra. And mind you, it is a clever kind of modification of so-called the Swinger trick, that Swinger constructed angular momentum algebra out of harmonic oscillator, two independent harmonic oscillators. So it is something like that in that sense. Okay, so under that you can define this Bell operator by considering two different systems with perpendicular spin orientations and consider their mixing at all. So each of these tensor product operators, we have to take the expectation values. For that, what we are thinking that if those are PT symmetric states and they are related through a correlation, there will be some signature in each of these terms, and there will be a contribution which is absent in Hermitian cases. But for that, the problem is that you have to evaluate this norm operator. Just to calculate these scalar products, you have to evaluate this charge conjugation operator, so-called operator, for each system for a given potential, which can be difficult. So I don't know how to do that as of now. Maybe for some simpler continuous system, it may be possible. So that is kind of the idea. So yeah, so like this is the summary in that sense, that PT symmetric systems generalize the norm, but still we can end up with a simpler scalar product which is not positive definite, but that is conserved, which can be considered as a non-local correlation. And that non-local correlation may be responsible for certain entanglement which are present in PT symmetric system and not in Hermitian systems. And to check that, there may be some prescriptions, but again, you have to determine the norm operator exactly, and which might not be very simple. Thank you.
Okay, thank you, Abhinav, for this nice talk. So the talk is open for the questions, comments, participants. Okay, can you go to the slide number 18? 18.
Okay, yeah.
Yeah, what is this PNL? Is it PNL?
Oh, PNL. So these are actually, so both PNL and TNL are some projection operators. So how you construct, so you know that if I take the integration from minus infinity to plus infinity, this is just the unit operator in the position basis. Right, but you are not doing that. What you are doing, that you are taking this integral from in an interval of length L, from NL to N plus 1L. So what are N? That N tends to infinity actually. So you are segmenting the whole real line or coordinate line in N number of, infinite number of segments of length L. So what happens that so this projection operator maps anything to that segment. If you cannot map, it is 0. So in that sense, it is possible.
There are two kinds of projection operator. What is the difference?
Yes.
between two?
Yes. So the T1 is a shifted one. If you can see, there is a x plus L term here.
Okay.
So that is kind of, it actually maps a shifted point to that same interval.
Okay.
So if you consider T dagger, it will be x minus L. So these are both projection operators.
Okay. And one more question. Go to the next slide. This dq by dt equal to 0.
Before that.
No,
This
next one.
Oh.
Next. I think 19.
Here?
19.
19.
Oh,
19. Okay. Oh, okay. So
the point is, you have mentioned that this dq by dt is equal to 0 and the constant will be coming out from that.
Yeah.
So as far as means, I know that this dq by dt is 0 means without any constant. Is it or
no? No. In that sense, what I want to so the condition is that if it is a constant and dq, see, consider the probability, normal quantum mechanical probability. You have dq dt. In that sense, q is the probability. So the probability is conserved. We say that, right?
Yes.
So in that sense, it's a constant. So we don't bother about anything. But it is a constant which is like defined at a single point. You consider a wave function at a single point, and it's all about that. But in this case, this q contains two wave functions at two different points.
Okay.
So you can define a wave function at any point independently. But if you say that if at two different points there is certain correlation between them, so that equation will lead to a constraint within the